Good morning. My name is Mbali Mpanza. I am a researcher from the University of Johannesburg. My talk today is on the geological mapping as well as the integration of the LIDAR scan. So this is what I'm going to cover on my talk today. I'll take you through the introduction, the geological mapping, looking at the traditional way of geological mapping. I'll also introduce to you the LIDAR scanning. The two case studies that we tested the LIDAR scan on, which is one, a gold mine in the Carletonville area, and also a platinum mine in the Rustenburg area. So then in 2020, towards the end of 2020, going early to 2021, we, together with the Advanced Ore Body Knowledge, the Mandela Mining Precinct, we embarked on a study to evaluate the scanning technology to identify the reef and geological features. So we were trying to see if would this be a possibility, and also try and improve in the geological mapping. So really the aim was to test the viability of the 3D LIDAR scanning, multispectral scanning technology, as well as the thermal scanning technology. So coming to the geological mapping, underground geological mapping for most of us geologists who do this on a almost daily basis in an underground mine, it remains unchanged. So we're still using your tapes, your field books, your Kleiner ruler, and that can be very mundane. So now the manual approach of geological mapping, like I mentioned earlier, is very laborious and time consuming. So the frequency of mapping in itself is rotational. So you find that some areas, some working areas have complex geology, and then in those areas you must spend time to map that specific area. But then now you miss the chance of going and visiting other working places because you've spent so much time in this one specific area that you need to look at, simply because it has complex geology. So in the mining industry, the LIDAR scan is commonly used by mine surveyors for the purpose of reconstructing mine accidents or a mine incident as forensic evidence. And also it's used by rock engineers when they identify the jointing or the fractures that occur in the hanging wall, so that they can characterize the hanging wall conditions. There are very good things that one can say about the LIDAR scan technology or the laser scanning technology. Number one is the fact that you can be able to capture the information or capture the features that you're trying to identify in a very short amount of time. So, and as we know, underground mining places, working places are quite dangerous. So with a laser scan or a LIDAR scan, you can just place it and set it up in a working area. For example, if the working area has very bad ground conditions, and you leave it there to scan without you actually going into the working area and physically being underneath that bad ground conditions or that bad hanging wall conditions. So really, as an aspect of safety and accuracy, a LIDAR scan is quite good. So now let me take you through to the case studies or the test mines that we went and actually tested the LIDAR scan on. The first mine we went to was a gold mine in the Carletonville area, which occurs in the Wits Basin, mining the Ventersdorp contact reef. So this is the mapping that was actually physically done. So the mapping was done so that we can compare with the LIDAR scan or the laser scan technology in terms of the measurements that we got when we were actually doing the physical traditional manual mapping versus the laser scan measurements, the point cloud data. So what we did here was map a reef drive. So initially we were supposed to map a crosscut, but the crosscut had already holed, and then we went through into the reef drive and mapped the reef drive. The ground conditions were quite intact, but we intersected one structure, a reverse fault, which threw the reef 0.7 meters. and it was striking northeast-southwest, dipping 80 degrees east. So we also, as part of the mapping, we profiled the reef. So profiling the reef is following the reef elevation on both sides of the fault. So now this slide shows you the scans. So this is the results, the images from our LIDAR scan. On the top image, you see on the dark area is the reef band. That's actually the Ventersdorp contact reef. So that's what was picked up by the scanner. What is good about this is you can actually read out the coordinates of the top reef contact from the point cloud data, from the scanned data. The bottom image is your crosscuts as well as the reef drive where we mapped. Shown there in green are the different points that were actually scanned, that were picked up by the scan. More scanned images. So if you really pay attention and get a close look at both the images, so the bottom image shows you the displacement, the fault. So you see the reef band, and there with that yellow mark, that's the position of the fault. So if you look carefully, you can see the Z elevation of the point before the reef was thrown up. And then also the Z elevation where the reef is actually up. Those two different elevations give you a value of 0.697, which is similar to the measurement that we made using our Kleiner ruler, where we said the reef is thrown up by 0.7 meters. And this is coming from the scan information. On the platinum mine that we visited, we picked up a prominent dike, which is 30 centimeters wide, striking northwest-southeast and dipping 80 degrees to the west. That is that picture that you see on the right-hand side. And then on your left-hand side, that is the scanned layout of the area, of the exact same area. And what you see as those blue and green and lime circles, those are the different scanned positions where the dike was picked up. So we did both the mapping and the scanning of the dike. What we also tried was do a thermal scan of the dike. So your thermal scan, the purpose of a thermal scan is to show you the different reflectivity indexes of the different lithologies of the different rock types. So what we did try the thermal scan, but it didn't really show us much in terms of the reflectivity indexes between both the different rock types that occur, your norites, your pyroxenites, as well as the Merensky Reef itself. So everything just appeared the same, and that is that top scanned image, which appears mostly blue or light green. And the bottom image shows you the scan of the actual reef, of the Merensky Reef. So what were the key findings from this exercise or from these tests? So what we found is that in both case studies, you could actually pick up the top reef contact or the reef intersections being identified by the point cloud, where you can pick up your X, Y, and Z and map out nicely your top reef contact. And also you can pick up the coordinates from the point cloud data of the dike structure or the fault structure that was mapped. And also with this information, you can now use a 3-point problem to calculate the strike of your reef, to calculate the dip of your reef, and compare these two with the actual manual mapping. And that's what we did in the two case studies. So what you will see is that from the calculated coordinates, from the elevations that we used from the point cloud data, we found that the dike actually dips at 84 degrees, and we had measured 80 degrees. So the variance is not that great. And then also we measured the Merensky to be at 8 degrees, and then the calculated from the 3-point problem, we calculated that the Merensky actually dips at 5 degrees. In conclusion, so the thermal scanning did not really give us much information in terms of the contrast or the reflectivity indexes of both the reef or the different structures that you intersect underground. So it really didn't work. We didn't achieve what we had set out to obtain from the thermal scanning. But from the point cloud data, we were happy that you can get spatial positioning and coordinates of your reef contacts. You can be able to calculate your dip and strike without actually physically being on that working place or measuring the dip and strike with your Kleiner ruler. Also, the Kleiner rule measured dip angles were comparable to the scanned calculated values. But there's future work, there's more work that needs to be done, and this includes the investigations into the automation of plotting the scanned point cloud data. So at this stage, we don't automatically plot. You still need to manually plot the information that you obtain. But then future work is planning on automating now this geology that you've picked up with your point cloud data. And also investigations to integrate visual presentation of the ground penetrating radar data, seismology data, as well as point cloud data needs to be looked at. I would like to thank you very much for your attention.